So finite differences. We're going to chat about something that we've kind of visited since grade 9. This might be sort of like a refresher for you. But it also relates to polynomials and how we can determine degrees if we have something like a table of values. So if we calculate finite differences, we will go until we get a constant column. And all I mean by that is the same number in that column. So I'm going to go and I'm going to calculate finite differences until we reach a column that is all the same. We usually do this when we're trying to classify like lines and quadratics and things like that. And that will actually tell us the degree. So as soon as I get a column with constant values, whatever that column is the degree of my polynomial. So in order to calculate finite differences, this just might be like a bit of a recap for us, but I will use the y's to calculate finite differences, and I will always do bottom minus top. So in order to calculate the first finite differences, I will do like the lower y minus the top y. Okay, and I will continue doing that sort of like all the way down here. So careful with your negatives and positives because we have a bunch of negatives here. I'm just going to grab my calculator now because I know I'm not going to do this well in my head. Okay, not a like super difficult process. It's just like subtraction, but takes like a little bit of time and just like attention to make sure that you are being careful with those negatives and positives there and are just entering in the correct numbers. If I mess up one along the way, especially like if it's in the first difference column or something like that, then also the second differences and the third differences will be messed up. So just be mindful of that, how that can sort of impact you all along the way if you make a little mistake. Okay, so I've got now my column of first differences. I can stop as soon as they are all the same number. So these ones are not all the same number, so I'm going to go to the next set of finite differences, which will be the second finite differences. And I use the first finite differences, and I just do bottom minus top again as we go along. So I'll do negative 37 minus negative 13. Actually, make this a little bit smaller here. Okay, negative 73 minus negative 37. Negative 121 minus negative 73. Whoops. And then negative 181 minus negative 121 should be negative 60. Okay, and again, I've gotten a column that does not have a set of constant finite differences. Okay, and again, by constant, I just mean I'm looking for them all to be the same number. That's it. So we're going to go on to third differences. If the third differences aren't the same, we'll go to the fourth differences, and so on. Okay, so let's just keep going until we get that row of constant values.
Where did we get the sheet last week?
So that was the package that I gave you guys on the first day. You should have that. Yeah. Okay, so getting negative 12 for the first one. We're on the end of lesson 3, Jalen. Okay, getting negative 12 for the second one. That's a good sign. and for the third one as well. So they're all constant. Negative 12, negative 12, negative 12. Perfect. I stop there. There's no need to go further. I now know what the degree is of this polynomial. If the third differences give me a constant value, then the degree of the polynomial that's represented by this table of values is degree 3. So the constant value that we get, no matter what column it is, has a relationship to the degree of the polynomial and to the leading coefficient. And the relationship is this. When I say constant difference value, I just mean essentially this value that we get in the column here. So the constant difference value of this table of values is negative 12. So I can get the constant difference value, or if I have the constant difference value, I can find other information. The constant difference value is equal to degree factorial, we'll talk about that in a second, times the leading coefficient. Okay, so what does this mean? Anyone in here take data management last year? Yeah? Some of you guys might know what this means then. Clayton, what does it mean?
Is it like, say it was like 3, it's like 3 times 2 times 1?
Yeah. So basically what factorial means is take that number and multiply it by every whole number below it until you get to 1. So if I have something like 5 factorial, it means 5 times 4 times 3 times 2 times 1. Okay? So factorial, multiply the number by every whole number below it until you get to 1. Okay, so if you wanted to do a little example for yourself, you can do it maybe above here if you have space. Example 4 factorial equals 4 times 3 times 2 times 1. So 4 factorial will be 24. Okay, I believe that most calculators do have like a factorial button on them. I don't usually use it, to be honest, because the degree is usually not high enough that I would need to do that anyways. Like it's quick enough to just do like 4 times 3 times 2 times 1 in my calculator if I need to. But I do believe that most calculators would have this factorial button somewhere. I actually don't even know where it is on my calculator. I'm sure it's somewhere though. Okay, so if I know 2 of these pieces of information, I should be able to find the third. In this case, above, I know that the degree is 3. We've determined that because the third finite differences are the same. And I know the constant difference value. So I could find the leading coefficient of the polynomial above, and that would help me find end behavior, and it would help me sort of know the general direction of my polynomial. So if I use this formula above, I usually just do the short form, like constant difference equals degree factorial, and then I'll use LC for leading coefficient. So I know the constant difference value from above is negative 12. We found that in our table of values. Whoops. Degree, we've determined that that is 3. So degree factorial will be 3 factorial. And then our job is to find the leading coefficient value. Okay, so negative 12, and then 3 factorial will mean 3 times 2 times 1, which will be 6. So all I need to do to get leading coefficient here is just, I'll divide out the 6. These will cancel, and leading coefficient will be negative 2. Zach?
Why do you put the exclamation point beside the 3?
So that's what we talked about above, which is it means factorial. So what it means is I will take the degree and multiply it by every number below it until I hit 1. It's like a mathematical operation, like a square root or like a squared or something like that. Okay, any other questions for this one? Kenzie? Yep. So if I know any two pieces of this, I can find the third piece of information. If I don't know constant difference, but I know degree and leading coefficient, I can find it. Yep, good point. Okay, let's flip over to lesson 4. Okay guys, so our goals for today, when we were doing like our first worksheet back last week, we had like a graph that, or we had an equation rather, that looked like this. P at x equals x squared, and then I think it was like x minus 2 or something maybe. And we talked about expanding that to see degree and leading coefficient. But when we graph polynomials, we actually like it to be in this form because we can see the x-intercepts more easily, and it actually tells us information about the x-intercepts. So we're actually going to learn how we could look at something like that and know some more information about it and actually graph something that is in factored form like this. If the polynomial is not in factored form, we do know some information about it still. We know end behavior stuff, and we know maybe like possibilities for turning points and possibilities for zeros. But factored form just gives us like a bit more of a picture of that. And in our next unit, we're actually going to learn how to go from standard form in polynomials that are higher than what we're used to. So in grade 10 and 11, we talked about factoring. Right? We went from x squared, things in x squared form to factored form. We're going to learn how to do that for higher degree polynomials. But for now, you would sort of have to have them in factored form in order to do this. So there's a couple of things that we need to know before we get into this. The first one is called orders. And anytime we look at a polynomial in factored form, we are going to look at the exponent that is on the x or on a bracket, and that is going to determine how our graph will react as it goes toward that x-intercept. So order 1, this is probably one that we're used to seeing. an order 1, and don't worry about this too much right now. We're just going to get this base information down, and then we'll look at some actual examples and pick out the orders and things like that. So order 1, if I have a polynomial that has an order 1, 0, the graph will essentially just go straight through the x-axis. So this is an example of an order 1, 0. Okay, and graph goes straight through x-axis. Okay, or slightly curved or whatever, but it will go right through the x-axis at that location. Okay, order 2 is almost going to look like quadratic shaped at that area of the x-axis. So what an order 2 will do is it will actually hit the x-axis at the x-intercept and bounce off. So it could look something like this. Okay, so think of it as if it like bounces off the x-axis. Order 3, so an order 3, 0, is going to do almost like what a cubic function does, and it sort of like goes toward the x-axis, but then goes through the x-axis in an S shape. So what this looks like is, if I have a polynomial, let's say maybe it looks like this, and then it's going to hit my x-axis. Sorry, I did that bad. Let's just do this. It's going to hit my x-axis and go through in an S shape. So something like so. Okay, this is order 1, goes straight through. This is order 3, goes through in an S shape. Okay, we're not going to go any higher than this into like orders 4 or 5, anything like that. If you're curious about it, you can always do some graphing, but this is sort of what we're focusing in on for this course. We will do some simple factoring today, so I'm going to remind you guys about like quadratic factoring and common factoring, but I wouldn't expect you to factor something that you've like never ever seen before today. So this one asks us, we're going to factor, identify any key information, so things like degree, leading coefficient, x-intercepts once we get this factored, orders, and then we'll do a sketch. So first things first, anytime I'm factoring, I always common factor first. Is there a common factor here? Kenzie? X squared. So I see that there are 2 x's in every single one of these terms. I'm going to common factor that out because I want to make my life much easier. Who doesn't want to do that? And then I will be left with x squared minus 4x plus 3. Now this is something familiar. We're used to factoring things like this. This is what we call an easy trinomial. And if I want to do easy trinomial factoring, I'm looking simply for 2 things that multiply to 3 and add to -4. Okay, so we're taking it back to some of our grade 10 and 11 factoring quadratics. Amelia? So this is just common factoring. So we took an x squared out of each term. So if I take 2 x's out of 4, I'm left with 2. If I take 2 x's out of the 3 of them, I'm left with 1x, and then I took out the 2 here, and I was just left with 3. Okay? So I'm just dividing out an x squared and putting it out front. Okay, so back to this. 2 things that multiply to 3 and add to negative 4. Bella? Okay, so multiplies to 3, adds to negative 4 would be negative 3 and negative 1. How do I use this to factor now? Remember, this is just an easy quadratic, so I don't have to do like a whole process here. Should be a relatively simple step. Like I should be able to go right into factored form, right? I have some hands going up and down here.
I know to do the long way.
No, we don't need the long way. What's the easy way? Emma?
I guess x minus 3x minus 1.
Yeah, put those numbers right into brackets right away, right? We don't have to do that whole long break down the middle and then do the groups and all that. We don't want to do that. Make your life easy, not hard. Okay, this is now in fully factored form. I have like everything in bracketed form. It's fully common factored. There's no common things in the brackets or anything like that. So I should be able to see the x-intercepts now. And if I look at the original standard form equation, I can see degree, I can see leading coefficient, and all of that good stuff. So here's some things that I want to know. We can fill out some of these. Degree, I want to know leading coefficient. Let's talk about end behavior, whichever format you want. I think we should be able to see maybe y-intercept here as well. And then we'll talk about zeros and their orders. So I think you guys should be able to fill out up to here. You can try out the zeros and their orders as well if you would like. But let's get these 4 filled in, see what you can fill in there. Okay, mostly you're looking at just the standard form original equation for this. Okay, what is the degree here? Remember, we're looking at the standard form for this. Keaton?
4.
Degree is 4. I'm looking at this, right? X with the highest exponent. Leading coefficient? Matt? 1, because in front of x to the 4, there is a coefficient of 1. Okay, end behavior, either notation. Nick? So because this is even and positive, this must go from quadrant 2 to quadrant 1. So I could even, if I wanted to, just pencil in those ends right now. Quad 2 to quad 1. What's the y-intercept? How do I find that like really quickly by looking at my polynomial? Michael? Yep, and what happens when I do that? Yeah, or in other words, if I don't have a constant here, it's like a plus 0, right? So whatever your constant is in standard form, that's what your y-intercept is going to be. Or if I'm not sure, I plug in zeros for the x's, as Michael suggested, and then I will get the y-intercept. So in this case, this is actually a y-intercept at 0, 0. I can plot that if I want, put that in. Okay, yeah, Keaton.
With the zeros, the maximum of 1 and then is that what you're asking?
So we're going to go into the actual coordinates of the zeros here. But you are right. It would be, or actually minimum of 0. Maximum of 4, minimum of 0. In this case, I have zeros here, here, and here. So I actually have 3 zeros. Could somebody tell me one of the zeros based on what you see in the factored form there? Clayton? 3 is a 0. So 3, 0 comes from this bracket. And I will know the order based on the exponent that I see on the outside of this bracket. What is the exponent on this x minus 3 bracket here? Sarah? 1, because if I don't see an exponent, I know there's like an imaginary 1 exponent there. So I'm going to say this is order 1. Okay, so we got one of the zeros from this. What is another one? Bella? There is one at 0, 0 from this. If I just have an x squared, that is a 0 at 0, 0. And the order on that is determined by the exponent on that x. So this will be order 2. Okay, the only time we get a 0 at 0, 0 is obviously if the y-intercept is 0, 0, and also if we have like a single x that's not like x minus 1 or x minus 5 or plus 5 or whatever. So you'd have to have like an x that was common factored out or something like that. Okay, and the last one. What is the last 0 here? Serena?
Would it be -1, 0?
Close.
0,
You were closer before. What's you got wrong, Michael? Okay, so just have to switch the sign that's in there, just like we did for 3. So it should be +1, 0. And the order on this, any ideas? Bella? Order 1, because this has an exponent of 1 outside the bracket there. Okay, I'm going to plot these 3 zeros. I already have 0, 0 plotted, so that's done, because that was also the y-intercept. This is just a general sketch, but if you can maybe just make a couple little ticks on here that are relatively equal in distance, just so that you sort of know where you're drawing each of these. Okay, so we have a 0 at 3. We also have a 0 at 1 and 0, 0. And I'm just going to slide this end over kind of like here, because that is, there's no x-intercepts on the other side there. Now we need to decide on what's going to happen in between here as my graph crosses the x-axis here. So the first 0 that I'm going towards is this one, the one at 0, 0. This is order 2. Based on what we talked about above, I know that my order 2 is just going to sort of bounce off of that 0, and it's going to go back up. 1 second, please. Okay, so I'm going to come toward this 0. And as I come toward this 0, I am going to bounce off of the 0 because it's order 2. So something like this. Okay, I'm not going all the way through this because order 2 is sort of taking the shape of a quadratic where it bounces off. If I have to now cross this, we have to make some judgments here, and we have to use our intuition here. Probably what's going to happen is I'm going to have to turn back toward this 0 now, right? Like the only way that that's going to happen is if I turn back towards it. And now I'm coming toward the 0 at 1, 0, and it's order 1. So based on what we talked about above, my graph is just going to go straight through to the other side of the x-axis here. Okay? So order 2 bounces, order 1 straight through to the other side. And again, I'm using my intuition to fill in the gaps here. I am probably going to have to turn in here, back up toward the next 0, right? This is my next 0, and I have to end up this way. So again, probably going to have to turn, something like this. And I'm coming toward a 0 that is order 1 again. So all I need to do now is just go straight through that 0, and I'm going to end facing up. Before anyone asks, I do not know how high and low these valleys and hills go at this point. That is what calculus is for, okay? If you wanted to, you could test a value in between. Like I could test maybe 2 inside here, and I could get a better idea of how low that valley goes. I could test like 0.5 inside here, and I could see maybe how high that hill goes. There's no guarantee that that's going to tell me perfectly where the turning point is, because The turning point could be over here, right? This doesn't necessarily have to be symmetrical. It could go like this. I don't know. You're just going to make sure that things are kind of nicely curved and that the x-intercepts are correct, that the orders are correct, and that the end behavior is correct. Okay, and the y-intercept as well. Is that what you were going to ask, Sarwa? See, I knew. Someone always asks me that. I always know. Okay, other questions on this? Zach?
Where do you see the zeros in that equation?
So once I get it into factored form, this form here, I can see the zeros in like the brackets. So this one gives me the 0 at 3, 0. This one gives me the 0 at 1, 0. And this gives me the 0 at 0, 0, because it doesn't have any value inside it with a bracket. Okay, so just as a recap, guys, when we had things like just in simple factored form, like x plus 5, x minus 6, I would typically, to find the zeros, I would set y equal to 0 to find where they cross this line. And then I have to decide what x I could plug in to make the whole thing 0. So it's usually the opposite of what I see in the bracket, because if I plug in, for instance, -5 in here, then I will get 0 times -11, and that makes the whole thing equal to 0. So I'm looking for all the possibilities of the x's that make my y equal to 0, because on this line, y equals 0. Okay, this is where y is 0, and then 1, 2, 3, and so on. So I'm looking for the x's that make the equation equal to 0. That's how we get the x-intercepts. Okay, so you need to have it in factored form in order to do this. Okay, I think we have time to get going on the next one here. The next one is like partially already factored for us. It says factor fully, we're going to identify key info, and then we will sketch. So this, there's not too much I can do with that. 3x minus 4, it's binomial. There's no common factor. X squared minus 9, does anybody recognize this as something? It's a special something. Sarwa? Close. Bella? Difference of squares. So perfect square is like perfect square trinomial. This one's difference of squares. So if I have a square here and a square here and a subtraction in between, I know this is difference of squares. How do I factor something like this the quick way? Kenzie? Mm-hmm. Yes, so you square root each piece of the binomial, and then you get 2 brackets. One will be plus, one will be minus, and that's what we get. Sorry, this is cutting out on me here. And then we'll leave the 3x minus 4. Why does this happen? Well, if we think about a trinomial, if I put in a 0x term here, what 2 numbers multiply to give me -9, but add to give me 0? Multiply to -9, add to 0. Matt? +3 and -3. So then if I factor this, I'll get x plus 3, x minus 3 because of that. Okay. Let's go through, now that we have this info. Also, guys, I want you to remember that this is not in fully standard form. This is partially factored already for us. So one thing that you should note is that the orders of the zeros actually always add up to the total degree. So if I look at all the orders here, 1, 2, and 1, when I'm in fully factored form and I have all the zeros, if I add them all up, I'm going to get degree 4 here. Okay? So if I don't have something in like standard form, one option would be is I can just expand this out quickly so that I can see it in standard form. But I also should know, based on all the zeros and their orders, what the degree is as well. So I'm just going to take 1 second here and I will FOIL this so that we can see all the other information as well. So x squared times 3x is 3x cubed. X squared times negative 4, negative 4x squared. Negative 9 times 3x, and negative 9 times negative 4, positive 36. Okay, so degree. Or actually, you guys can take a second and fill out maybe some of this information. Okay, and if you want to try the zeros and their orders, you can try that as well if you get there. We've got 1 more minute here, and then we'll do the break and continue afterwards. Just resume it now. Okay, so we're looking at, just as a recap for the video here, we're looking at each of the brackets to determine the zeros and the exponent on that bracket to determine the orders. So we found negative 3, positive 3, and if we set 3x minus 4 equal to 0 and solve, we get 4 over 3. This is also order 1 because of the exponent. And now that we've filled in all this info, we plot and then just sort of connect the dots of everything that we've found. All right, we are going to try one more of the graphing here. Identify key information, sketch the graph. This is in fully factored form for us already. We don't have to do any factoring on this one. I have all the brackets, the exponents are on the outsides. I have a single negative 2x here, so I can find degree. Leading coefficient, I can find the intercepts as it is. So I'm going to show you guys a little, rather than having to expand something like this out, I'm going to show you guys a little trick to find the degree and the leading coefficient. So the first thing actually that I want to do in this one is I want to find the zeros and their orders because that's going to help us with our degree. So let's start with that since we're in factored form. Wherever you see an x should produce some kind of 0. So this will produce a 0. This will, oh, I wanted a different color there. This will produce a 0. And this. What makes negative 2 times x? So what value of x will make negative 2 times x equal to 0? Okay, I'm just going to ask one more time so you can think about it. What value of x would I plug in to make negative 2 times x equal to 0? Clayton?
0.
0. So if I have negative 2x and I want to know where that equals 0, negative 2 times 0 equals 0. So x equals 0 for that one, not positive 2, right? So the first 0 is going to be found at 0, 0. What is the order on this one? Matt, what do you think? Order 1, because I see an exponent of 1. Or I don't see it, but I know there's an exponent, an implied exponent of 1 on there. Okay, next one. The one in the green here. Michael? Okay, perfect. So it will be found at 3, 0. I switch the sign that I see in this bracket and the order. It is 3. Okay, exponent of 3 on this bracket. Perfect. Last one. Jacob?
Is it negative 5?
It is negative 5. Any idea on order for this?
Order 2?
Order 2. Perfect. Exponent of 2 on the outside. Okay, if I'm in fully factored form and all of these x's have zeros and orders, or all of these x's, I found all the zeros and I look at their orders, that's going to help me decide on degree here. So if I want to find degree by not having to expand, sorry, Keaton, question?
I was going to say,
Oh, go ahead. The degree will be 6, yes. So if I add the orders, of zeros in fully factored form, I should get the degree. So 1 plus 3 plus 2 will give me a degree of 6. Okay, that's the quick way to do this if you're already in fully factored form. Ideally, I do not want to have to expand something like this because it's going to take a really long time, and I want to make my life easier if possible. So that's going to help us with degree. The quick way of finding leading coefficient. So leading coefficient, you are going to multiply all coefficients on x's. This is only if you're in factored form, okay? So maybe I should just make a note that this is in factored form. Multiply all coefficients of x's and apply their exponent if they're in a bracket. Okay, so in this case, I have a coefficient on an x here. It's -2. What's the coefficient on this next x? This one. 1. And technically, because this has an exponent other than 1 on the bracket, I should also apply the cubed. Obviously, I know 1 cubed is just 1, but just for the visual here, so that you know what you're doing, if it has some other number. Okay, so here's a coefficient. Here's the coefficient. Last one is also a 1. Okay, we know there's like an imaginary 1 in front here. And I would always be applying the value on the bracket. So I will be squaring that. Irrelevant when it's 1, but if it's another number like 2, that's important, right? So I'm going to get -2 times 1 times 1, and that will give me a leading coefficient of 2. Alternatively, if I wanted to, I could expand this whole thing. This would be difficult to expand. It would take a while, but it's just multiplications, right? So we could do it if we needed to. Okay, last two things, end behavior and y-intercept. What is my end behavior now that we have degree and leading coefficient? Bella? Quadrant 3 to quadrant 4. We know this because it's even, so either they both face up or they both face down. And we just found that the leading coefficient was -2. That would be important because now I know that both the ends are facing down. Michael said something earlier about finding the y-intercept. If I want to find the y-intercept, but I'm in factored form, I need to evaluate f at 0. Now, I don't really need to do that for this one. Why do I not need to do any evaluating for this one in particular, for y-intercept? Keaton? I already have a 0 at 0, 0. That will be an x and y-intercept, right? That's the same point. But if you're in factored form, evaluate f at 0. Sub in 0 for all the x's, see what you get. In this case, we will get 0, 0 for a y-intercept. We already have that here. As soon as I have an x-intercept that's 0, that's the y-intercept. Okay, so let's fill in what we know. We know 0, 0. We know 3 and -5. So 1, 2, 3. 1, 2, 3, 4, 5. Okay, so probably my end is going to have to start a little bit further over here. And let's plot those before we start as well. There's our zeros. We start facing down. Okay, let's note the zeros as we come toward our intercepts here. So first intercept that I'm going to be approaching from the left is at -5, and it's ordered 2. So what do I do when I hit this? What did we talk about at the beginning of this lesson? I would come towards it and here, I have to bounce off of it. So I'm going to come toward it and bounce down. like so, something like this. Okay? What's going to happen in between here? I see my next intercept is at 0. What's going to happen as we come toward this, Matt? I will go straight through it because it's order 1. And Clayton? I'm going to have to turn somewhere in between here, so I don't know where. I will turn somewhere, and I will go back up towards 0, and I will go straight through it because it's order 1, as Matt said. Okay, probably not even that high because I'm going to have to turn back around to hit this, right? So my mind is telling me we're going to have to turn back this way. As we approach 3, we are now sketching something that's in order 3, 0. So this is a little bit different than what we've seen before. Surwa?
You turn and go back down in that shape.
Okay, so you might have to practice this a little bit, but you're going to come back through here and just through in an S shape like so. Okay? Something like this. Okay, if it's more pronounced or less pronounced or whatever, just do it the best you can. I would say probably something like this. Okay, and you can make yourself a note if you need to. This is S shape for order 3. Okay, so that's generally what our polynomial looks like. Again, do I know if this is like this? I don't. I really don't. Once we do calculus, we'll be able to identify those values a little bit better and exactly where those turning points are and all of that stuff. Can I clarify anything for this one? Okay, so I just want to remind you, maybe we'll make an extra note on here. This is only for factored form. Is where we add the zeros, and again, only in factored form, where we take all the coefficients of x and multiply them together. Okay, we don't need to do this. If we're in standard form already, we should be able to just look at the degree and the leading coefficient and pick that out. Surwa?
So when it's possible to factor out?
Yes,
Okay.
because otherwise we won't be able to see the x-intercepts properly. And that's only if we're like trying to sketch and trying to identify the zeros and their orders and things like that. If I'm just looking for something like degree, leading coefficient, and behavior, I want standard form ideally. Okay. We're almost to the end here. We'll have some time to work today. I don't know if we'll get to the last part of lesson or to any part of lesson 5. We'll see how the practice is going. But for sure, we're going to finish this up. Okay, so our job is to create a polynomial with degree 3. And I want zeros at positive 5, positive 3, and 2. And I want it to pass through the point 1, 24. Okay, so if I have degree 3 and I have 3 zeros, what do I automatically know about the orders of each of these zeros? I'm just going to say it one more time so that we can think about it. If I have degree 3 and I have 3 different zeros, what do I know about the orders on each of these zeros? Serena.
I'm not sure, but I think they might all be 1.
Yeah, they're all order 1 because we know the orders should add up to the degree if it's in fully factored form. So I know now these are all order 1. So here's my polynomial. We'll call it p at x. I know I will have 3 brackets. I'm going to leave a little space here for now. I know I will have 3 brackets to represent these 3 different zeros. They will all have an exponent of 1 on the outsides. And what will these brackets look like if I want them to represent x-intercepts? What should they look like in an equation? Keaton?
Would it be like x minus 5, x minus 3,
Perfect. I will switch the signs of all of those, and I will put them in with an x to represent all the 3 zeros. And then I have this extra piece of information. It passes through the point 124. So I need to maybe sort of pretend here that there is some unknown value here that I will solve for using this point. Kenzie, what would you do?
I think you solve the x to 1 without the x and without the x's in the equation and from the y.
Yeah. So we're going to actually, this is x and this is y, or in other words, this is p at x. So I'm going to actually evaluate p at 1. I need to put this unknown k because that's sort of, it's like a stretch or compression factor, right? That's sort of what will make my graph pass through 124. So that's kind of an unknown I need to solve for using the point. So I'm going to plug in 1 for all the x's. And then what is p at 1 equal to? What is y when x is 1? Clayton?
24.
Okay, so I will sub in 24 because I know the polynomial's value when x is 1 is 24. And then I'm going to start simplifying here. So -4, -2, -1. This is just multiplication. So I get -8, k. And then we divide to solve. Did I do something wrong, Clayton? You looked like I was doing something wrong. Did I do it right?
Yeah.
Okay. Okay, so we get -3 for k. We sub back into our original equation for k. So p at x equals -3 times our 3 binomials that represent those x-intercepts. Is this an x-intercept? Does this tell me information about an x-intercept? The only reason we need this, doesn't have an x with it, right? It's not an x-intercept. The only reason we need this is to fill this criteria, that it goes through 124. If I didn't have that, then it might not go through that point. Okay, so it's just like a stretch compression type factor that makes it go through this point. Amelia?
If the order came to add up to the degree, and
Yep.
let's say the degree was 4, does it matter which one you get, like order 2 instead of order 1?
If it has to go through a specific point, then like maybe potentially. If it doesn't say, then you just make one of them order 2.
How would you know what it does?
So I will either tell you this specific 0 is order 2, or it's left a little bit more open. So I think the next one is a good example of this. It says you are going to create an equation that's degree 5, and it only has 3 zeros. And you're going to sketch a graph of this function. If you need to, you can use graphing software to help and test. But in this case, if it's degree 5 and I only have 3 zeros, there's multiple answers for this one, right? I could have different combinations.
And it doesn't matter which one is what order?
Not in this case. Unless I specifically say this one's order 3, this one's order 1, like that idea. Good question. Okay, so you, and if you would like to work with the person next to you, you can stay in your desk and just discuss. You guys are going to create an equation, polynomial equation in factored form. It needs to be degree 5, but it only can cross the x-axis at these 3 values, 5, 1, and -5. Okay, and then you're going to create a general sketch of your function. Okay? So create the equation, create the general sketch. If you need to, you can also use graphing software to help you sort of test and develop your equation. So I'm going to give you guys a couple minutes to do that, and then we'll talk about some options. That's here. I would like a couple people to share what their equations were. Clayton, what did you come up with?
P at x equals x plus 5 squared, and then x minus 1, and then x minus 5 squared.
Okay, so I have the 3 different binomials representing 3 different terms here, or 3 different x-intercepts. The orders on these add to 5, so 2, 1, and 2. So then I get degree of 5. Perfect. If I were to do a sketch of this, I would have 0 over here at -5. I would have a 0 over here at +5. I would have a 0 at 1. So note that Clayton changed the signs of each of these as he put them in the brackets as well, so that was good. And because this is an odd degree, and in this case we would have a positive leading coefficient, we have 1 squared times 1 times 1 squared. Okay, so there's no negatives on any of those x's or out front. So I'm going to have negative and positive, or sorry, negative and odd. So I bounce as I go toward -5, because this has a squared on it. Then I have to turn somewhere in here. I go right through 1, because that has an exponent 1 on it. And then we will come back toward 5 and bounce and end facing up. Okay, so both of the ones with ordered 2's that Clayton created here, they bounce. Okay, another one. Who else had a different one? Serena, what did you do?
I did x minus 5, x minus 1, and then x plus 5 to the power of 3.
Perfect. So this also works. If I add the orders 1, 1, and 3, I have a degree of 5. Positive leading coefficient, again on this one, because I haven't put any negatives in front of the x's or anything like that. So if we were to graph this one, so same locations of the intercepts here, so 5, -5, and 1. Except this time I go straight through, so same end behavior as well, odd and positive. This time I go straight through I guess -5 is the one that has the order 3. So I'm going to go through in an S shape at -5. Okay, I'm just doing this one quickly because everyone has different ones here. I have to turn back down toward 1. Okay, that's this x-intercept. And then +5 has an order of 1, so I must turn back around and end up here. That is possible as well. If I added in, let's say I added in a -2 here. What do you guys think that changes about this? Clayton?
Instead of it being quadrant 3 to quadrant 1, it would be quadrant 2 to quadrant 4.
Yes, so then that's going to change my end behavior because I now have added in a negative multiple out front. And it's going to stretch it by 2 as well, so it'll be like two times more stretchy, more stretched. Okay, same zeros and stuff like that though, but it's going to go like through here, it'll be more pronounced, and then like so. Any other combinations that you guys came up with for equations? I'm not going to do all the graphs and everything, but any other different equations that were out there? Michael, what'd you put?
I did fx equals x squared, bracket x minus 5, bracket x minus 1, bracket x plus 5.
Okay, do you guys agree or disagree? Does this fit? Is it degree 5, first of all? And does it only cross at 5, 1, and -5? Those are the two stipulations in the question. Bella? Okay, so this produces an x-intercept at 0, 0. The question says I only get to cross the x-axis at these 3 values. So I can't have an extra x out here. I only can have 3 x's. That's a good point. So instead, we must have these 3 brackets. We cannot have any additional x's. But I could have any combination of exponents on these that add to 5. Did someone do something else different than what we've seen so far? Bella, what did you do? Okay, perfect. So I have exponent 1, exponent 2 equals degree 5, and it also does not have any additional x-intercepts there. Okay, I'm not going to do the sketch for this one, but you guys get the idea. This one was more of like an open question with a variety of answers.